So what we're going to do is start with the slope of the secant line, and then we're going to try to use that to get at the slope of the tangent line, and that's going to be how we define the derivative. So start with the slope of the secant line. We have just general generic slope formula. We'll call this point 2. What's the y value of this point? There it is. So if you want, hey, what's the y value? Line this point up with the y-axis and see what it is. So this point lines up to this y value on the y-axis. That's f of c plus h. So y2 is f of c plus h. And then y1 is based on the first point. That's a point of tangency. And that is f of c. We have that right there. And then what are the corresponding x values? So what's the x value corresponding to this point? C plus h, just line it up with the x-axis and see where you are on the x-axis. And the first point, the x value is c. Now, looking at your denominator, what can you do? Yeah, you can look at these c's and say, I can cancel those out. And so you're left with then f of c plus h minus f of c all over h. Now, that should look semi-familiar. What have we seen before that's a lot like this guy? Yeah. So all we've done is swap out x, which is just kind of like a generic variable, could be anything, for a c, which is like a specific value. Okay, now we're not just saying any old x, we're saying that x, we're calling it c. Other than that, it's the same thing as your difference quotient. Now, back to here, that's just your secant line, and h is just the distance from one x value to the next x value. So h could be pretty much anything. We could make h really big and connect this point to a point way out here on the right, or we could make h really small and connect this point to a point right next door. And if we're trying to get at the tangent line, what we're going to do is make h really small, because a tangent line is a line that connects the point basically to itself. So if we bring this point and imagine bringing this second point closer and closer and closer and closer to the point of tangency, what's happening to h? It's getting smaller, and that is the idea of what we just did for like the last 3 weeks. Like, that's a limit. So what we do now is we take this formula and say, let's take the limit, and what are we doing with our h? H is going towards 0, so that this point, c plus h, is heading towards c. So we're going to bring this point down the curve so that it's closer and closer to the point of tangency, because our goal is the tangent line. And as we bring these points together, h gets tinier and tinier. H heads towards 0. So we're taking the limit as h heads towards 0 of this thing. And it turns out that is exactly the same thing as the slope. So if you succeed in taking that limit, what you've done is you've successfully found the slope of the purple curve right at that point, wherever c is. And then if you want to do it more generically, with any old x, instead of a specific value c, then you have the derivative equation instead of a derivative at a point. So this right here is slope. That's called the derivative of f of x at x equals c. And the notation for that is f prime of c. So ta-da. So there's your derivative equation. You've already seen this before, sort of, but with like a generic x instead of specific c, but it's the same thing. So in the notes, it's going to kind of lay things out in a more systematic, organized way, because that's maybe a little bit of a jumbled mess. But that's what's going on. The goal here is, hey, what's the derivative? In other words, what's the slope of the curve at a particular point? And that slope is the same thing as the slope of the tangent line that connects that point just at that point. So this red line is touching the curve at that point and only at that point. Unlike the secant line, which connects this point up to the second point along the curve. Questions with that? All right. So let's go back over to the notes. And look at some notes. So we got to be clear on what's a tangent line and what's a secant line. Lucas, could you turn off the light again, please?
Sure. Could you the camera?
Say again? Oh, camera? Got it. Did you want the camera back over?
Wait, no. Yeah, I was going to see that.
You want it?
Sorry?
Do you want it back where it was, or is it good where it is?
What were you saying?
I'm asking you what you were saying.
It's fine where it is now.
Okay. My mic is being horrible today for me being able to hear other people. So if you want to say something, put it in the chat and then shout at me. All right. So tangent line is just any line that connects to a curve at a single point. And then you can just kind of look at the tangent line and kind of make an eyeball guess as to what's the slope of that line, and that's the slope of the curve at that point. So here, you got a parabola-looking thing, and then you've got this tangent line to the curve at this point P. So here's P, and then we drew the tangent line to the curve at P. What's the slope of that line? Zero. How do you know it's zero? It's a horizontal line. And so that tells us the slope of the curve is zero when you're right at that point. We can look at that and say slope is zero there. Second example of a tangent line, we have a curve coming down doing one of these things. Looks like a kind of upside down cube root graph. And then the tangent line passes through the curve, but it only hits the curve right at that point only. And it's kind of like parallel to the curve. So here's the tangent line passing through the curve in a way that it's kind of parallel to the curve at this point. And what can you tell me about the slope here? Is the slope zero? No. Do you know what the slope is exactly? No. Can you tell anything about the slope at all? It's negative. The curve's going down. So back in Algebra 1, you learned, all right, a negative slope means the line is falling. So here, a negative slope for a tangent line or a negative slope along a curve means that the curve is going down at that point. And then a third example here, you got a tangent line connecting to this point here at P. Now, you might say, hey, wait a minute. This curve bends so that if we extend the tangent line, it hits the curve again down here. So isn't this technically a secant line? And yeah, you have a good point. But if you just look at this little section of curve up here, on this little portion of the curve, the line only hits that curve once, and the only reason it kind of hits the curve again is because the curve cheats and like kind of bends to get in the way of the line. So this is a tangent line to the curve at P, and what can you tell us about the slope here? It's positive, right? And you can see it's positive because the line is going up, and similarly, the line itself, the curve itself, f of x, is moving up right at that point. So later on, when we do analysis of functions using the derivative, this is going to be much later. So chapter 2 is all about finding derivatives and doing a little bit of work with them. Chapter 3 is going to be all about using derivatives once you've found them. So this is kind of like a chapter 3 thing, but once you have the derivative, once you have the slope of the curve at a point, you can use it to analyze the curve in all sorts of ways, just knowing whether the derivative is positive or negative. All the stuff in italics up here, just read it, don't write it down. So, tangent line connects to the curve at a single point. Secant line connects a point on the curve to another point on the curve, like we did on the example over there, introducing this. And then, when we take the secant line and kind of bring one point closer and closer and closer to the other, the secant line approaches the tangent line in terms of what it looks like. And again, this stuff down here that is in italics, don't write that, please just read it. Does anybody need more time with this? How many of you guys in here are seniors? I want to congratulate all you seniors on not having to go down to the cafeteria for that work-based learning thing that they're making all the seniors do. Yay for getting that done when you were told to. Well, I think it's a graduation requirement, so. Yeah, there's one more box to check for the state. Harrisburg says you got to do this and this and this and this. So this is one of those boxes that we have to check off to make the Harrisburg happy. Yeah, don't be like him. All right, can I scroll? I guess so. So, boom, definitions. Know your definition for the tangent line, the slope m. And we're going to do a lot with the slope itself, and we're going to do a lot with the tangent line. So that's worth writing down for sure. If you have a function and it's defined on some open interval, and if this limit exists, so the triangle is code for delta, and that means change. So the change in y over the change in x, that's your slope, and then it's spelled out in detail, and we always use h in place of delta x. So that's why over there when I introduced this, I used h instead of delta x, because that's going to be what I use when we do work, because it's a lot easier to work with. So if this limit exists, then the line that goes to the point c comma f of c, so that's your point of tangency, and that has the slope m, where m is defined like this. That line is your tangent line to the graph at the point c f of c. So I'm going to try to draw this here. So there's your point c comma f of c on some curve. And then here's the tangent line. So the red line is your tangent line to the curve at the point c comma f of c. We call that the point of tangency. And then this limit is the slope of that tangent line. And what you would do is if you wanted the equation of the tangent line, you would get that limit, here's your slope, and then use this point and put them together to write the equation of the line. So a lot of what we're going to be doing here is going to be finding a slope using the derivative formula, and then using the slope and the point of tangency to write the equation of the line. So like all that time at the beginning of the course, back in like January or February, of writing equations and lines, this is why. So you should write down to here. And then I think that's going to be it for our notes for today. And you should notice the relationship between this formula up here for slope and this formula right here for f prime of c, derivative. Let's see, they're kind of the same thing. For this third thing here, where it says more generally, f prime of x is the derivative of f, and that formula for that limit is the same thing as these other ones, except now we're just replacing c. C is a specific value, so c could be 5, c could be 3, c could be 1, but c is always a number that's given to you in a problem, where like that's the x-coordinate of your point of tangency. Here we're replacing c with just a generic x. X is just your variable x. And then the result is this gives you a new equation. F prime of x equals a new equation of x. Whereas up here, f prime of c is always a number. So f prime of c will give you a number for your slope at a particular point. F prime of x will give you a new equation that you could use to find the slope anywhere at any x value along the curve. And then this is just different ways of notation. So we have a lot of ways of expressing derivative with symbols. We can express the derivative with this f prime as like the apostrophe thing of x. We can call the derivative dy dx. I know it's dy over dx, but for whatever reason, we always say dy dx, even though it's dy over dx. I don't know why we call it that. Instead of f, if we're just dealing with like y equals equation, then the derivative is y prime. Or if you want to indicate I'm taking the derivative of a function, d dx of f of x. Means the derivative of some function f. So all of these are pretty much the same idea. They're all saying you're dealing with a derivative of something. There's other ways as well to express derivative that like we're not going to use ever, but that you, I suppose, might run into in physics. And if you do, your physics professor or teacher will tell you. Different situations make one or other of these more or less useful. So all that stuff there at the bottom, that should be italics. But all of these, if you see any of those, you should recognize, oh, that's just another way of saying the derivative. So none of these should confuse you when you see them. You shouldn't look at that and say, what does that even mean? It just means the derivative. It's just another way of saying the same thing. Like I can call you by your first name. I can call you by your last name. I can make up a nickname for you. I can call you Mr. Whoever. It's the same sort of thing there. What's up, Prince? Is that better? All right. Does anybody need more time with the notes? Okay. Prince, do you need more time? All right. Lucas, would you please turn the light back on? Thank you. So, over here, example 1, we want to find the slope of that function at the point 2, 1. Now, first off, what do you notice about that function? What kind of function is this? Linear. And since it's linear, what do you know about the slope? It's positive. Can you tell me specifically what the slope is? 2. It's 2. So you could look at this and say, hey, I know the slope is 2 because it's a line. And mx plus b tells me m is 2, slope is 2, done. But we want to make sure we understand and use and can set up the limit formula for the derivative. So the limit formula for the slope of the tangent line. And so we're going to do that. So start with writing down the limit definition of the slope of the tangent line. So this is going to be f prime of c, because the slope m is equal to the derivative at c. They're the same thing. And the slope formula is f of c plus h minus f of c all over h. Oh, I forgot something. What did I forget? What's missing here? Limit. So the limit, as h goes to 0, of that whole thing. And in this scenario, what's our c value? What is it? 2. Yeah, say it with confidence. And if you're wrong, so what? All right, so yes, it's 2. So C is 2, and then f of C here is 1. But we care about C. So C is 2. So we can take 2, plug it in here for these C's, and say, all right, we don't want just any old slope. We want the slope of this function at 2. And later on, when we're looking at things that are not lines, that'll make a difference. So we'll replace all the C's with 2. Now we need to be able to set this up properly. So here, I'm going to show you what's going to be the biggest issue is setting up f of 2 plus h. Here's what it's not. So what I saw on the test yesterday for something similar was when we had like f of x plus h, people were writing f of x and then just adding and tacking a plus h on the end. So if you see like this, that ain't it. All right, this is not f of x plus h. This thing makes you go into the function, and where you see x, you take out the x and you put in a 2 plus h. So not this thing. Don't just tack a plus h on the end of the function. So when we go to set this up, we have the limit as h goes to 0 of, what's our function? 2x minus 3. Instead of x, what's going into place of x? 2 plus h. So you're replacing the x in the function with a 2 plus h. This whole thing right here is f of 2 plus h. And then you subtract f of 2. That's just same thing. Now you take in the function and you take out the x and you put in a 2. So what's that going to look like? Okay, so somebody's already saying, I've done it, and it's 1. Let's set it up. So 2 times 2 minus 3. And yes, you absolutely, eventually that'll just be 1. So that's your setup. For a lot of us, that's like the first hurdle we got to clear is set this thing up correctly. Understanding what's going on with this 2 plus h business in the actual equation. Any questions with the setup? Why can't you just put 1 here? You absolutely can. Because you're not always necessarily told the point. Often you are, but not always. So I just want us to be used to that. And when we get into things more generic and we're doing f prime of x for any x value, then you're going to be dealing with 2x minus 3 again. All right, now we got to clean up the numerator. So to clean up the numerator, you guys can do that. What's the numerator going to look like when I distribute? Before 2h? 4 plus 2h minus 3 minus 1. Because you can look at that and say, that makes 1. And then what happens? So stay in the numerator. What do we do now? Add these all up, and what happens? They all cancel, because 4 minus 3 is 1, minus 1 is 0, and you're left with 2h. And then what happens? The h's cancel out, and we're left with 2. What's that 2? That's the slope. So that's the slope of the tangent line to the function at 2. And you just check. I already knew the answer because this is a line. Hey, we got it. And if you want the slope of the tangent line, well, that's not very interesting. Oh, that is the slope of the tangent line. If you want the equation of the tangent line, you would take that and combine it with the point of tangency and use those to write your equation. Let's look at example 2. Before we do, any questions here? Yes. How would you do it without? Later. Yeah, there are shortcuts. We'll get to the shortcuts after I've dragged you through the mud here for about a week. Because, Lucas, you don't seem pleased. Because this really drives home recognizing this formula, because here's the kind of question we can ask you. I can ask you, hey, find this limit as, that's that's an h, goes to 0 of something ugly, say of like sine of x plus h minus sine of x. Do you want to do that limit? No. So you need to recognize what this limit really means. This is f prime of x, where the function is your sine function. If you can recognize what this limit really means, that this is that, then you can say, oh, I know the derivative of sine because Edgar taught me what the derivative of sine is. I haven't taught you yet, but I will. And then you can say, I don't need to do all this limit stuff. I can just say, I know what this limit represents, and I know the derivative of sine, boom, cosine, done. But you're not going to learn to recognize this thing for what it is unless you see it a bunch of times. So you have to see it a bunch of times. And the only way you see it a bunch of times is if you're forced to actually do it. So that's what the next week is drag you guys through this thing. And then we'll say, all right, let's do shortcuts. And the rest of chapter 2 is shortcuts. So 2.1 is introduce yourself to the derivative and see how this works. And then chapter 2.2 and 2.3 and 2.4 and 2.5 is shortcuts. And there's a lot of shortcuts to keep track of depending on the situation you have. 2. Which point do you want to do first? Fauza, pick a point. Seems like a good place to start. This is the first one. All right, so we'll look at that guy. And for that point, Ahmed, what's our C value? 0. So we're going to do this thing for C equals 0. So slope of the tangent line is f prime of C. Call it f prime is 0. So I always write m is f prime because I want to build this connection in my head between the slope m and the derivative f prime because they are the same thing. So when you see m, you should think f prime and vice versa. Start to build that connection now. So always write m equals f prime of whatever. And then we have a limit. And let's just set up kind of the generic limit. What's our generic limit for the slope? F of C plus H minus over H. And then what the hell is H? H. And then what is our C value? 0. So we'll go ahead and make all these C's 0. Then you go into the actual function and say, okay, what's our actual function this time? Let's set this up using our actual function equation. And then this is where we got to be really careful about what we do with 0 plus h and where does it go and all that stuff. So f of 0 plus h with our function x squared plus 1, what is that going to look like? Plus h squared plus 1. So that is your f of 0 plus h bit. And then you're subtracting f of 0, which is, so not x squared plus 1, 0 squared plus 1. And it's all sitting on h. Now what? So what's 0 plus h? H squared is h squared. Plus 1 is plus 1, and we're subtracting minus 1. So now what happens? Ones cancel, and you have h squared over h. So now what happens? H's cancel out, and you're left with h. And now we got to remember we're taking a limit. Don't forget that you're taking a limit. Sometimes people do all the algebra, and they get their algebra done, and they think, great, I finished my algebra, I'm all set. And they forget to actually take the limit. So take the limit, and what do we get for our limit? 0. So our slope there is 0. What that means is that the curve is flat momentarily at the point 0, 1. You've reached the point on the curve where it briefly flattens out before it continues on its way. What are we at here? Well, we got plenty of time. You guys, on your own right now, do the same thing for -1. Now, this is going to be a little more work. Kaza chose for us to do the easy one together, so you guys get the harder one. So you guys do this for -1, and what's going to happen over here when you have -1 plus h all squared? You got to distribute that out. So you guys try that, see what you get for that. It's not going to be m equals 0 at the end. You want to know what the answer is so you can tell whether you got the right answer? It'll be -2. And then if you got that, jump over here to number 30 and set up the limit that you'd have to do for the point 5, 2 with that function. So when you guys go to do this part, you set it up and you see that you have to do -1 plus h squared. Don't call it 1 plus h squared. Right, that's going to be a mistake that some of you make. So remember, this is what it means. Think about what you get when you distribute that out. H always approaches 0. The goal is to bring like the second point to the point of tangent, so the distance between them always goes to 0. So H is always approaching 0. That negative 1 is just C values. So then the other thing is when you set this up, that's the negative 1 plus H is that thing plus 1. X squared plus 1, so there's your X squared plus 1, which is X. Okay, so now, set up the rate. If that were 4 times H, it's actually 4 plus H, and simplify it. So at this point, you rationalize the numerator. So you multiply by your times. Cool, so try setting up. Yeah. Alright, so we did the same thing as E1. So we set this up 3, and then if this is 4 times H in there, you can pull out 2. But you turn adding multiplication, because that's a plus or it's minus. This is stuff. There it is. So this would still be a square root of 4 plus H, and then you have to rationalize the numerator. So that's why you have to rationalize. Because if you plug in 0 right away, you get 0 to 0, so you rationalize. In your folder for today, I have homework that's officially due tomorrow. Practicing this. I think we should have more practice in class so that you don't go and make a hash of that. So that's not due tomorrow. I have to go into the folder and adjust that. But the homework that you see in today's folder, whatever it says there right now, I'm going to go and change it. It's not due tomorrow. Normally I'm going to say it's due Thursday, but I won't be here Thursday. So I guess that'll be on Friday. And then tomorrow we can practice in class.
That's crazy. Right. Even when you don't want them to be. Who's that? That was for you.
I got somebody's message about not know was here.